Hello and welcome to this short presentation entitled How to Present a Calculation. I've used the example shown on the slide here in a previous video to show how to lay out a calculation in a reasonably professional manner so that it can be clearly followed and understood by other engineers. What I'm going to do in this lecture is show you the way I format the calculation using my word processor. All calculations these days must be word processed in a very presentable way. And with all my calculations, I tendency to structure them in what's termed tables, as opposed to actually using an equation editor. Here's a presentation overview. We commence with a brief introduction. We outline the use of inserting symbols into our descriptive text or numerical calculations. And the insert symbols option is built into our word processor. It allows us to insert Greek symbols or mathematical symbols into our solution. Next, we recap the precedence rules, often stated through the mnemonic BODMAS, and also recap the rules and the laws of indices, both of which we'll be referring to within the development of our solutions. We must always comply with the use of BODMAS, our order of precedence of the calculations, and the use of indices help us simplify formulae or equations, particularly when using one-line formatting, which we will be using within the presentation here. Next, we have the main essence of the presentation. I show the word processing of a solution to a stress analysis calculation. It's a very elementary calculation we've used in the previous presentation, but it does allow us to outline the various steps involved and how to word process the steps in a clear, coherent and concise manner so that other engineers can easily follow our solutions. I will be using the table format throughout to develop my solution. I next include a small section related to formatting of formulae and equations on one line to reduce an equation that might be given on two lines, as shown here, and write it on a single line in what I've termed one-line formatting. The one-line formatting is preferable when using the table method of presentation, as I will be using. Finally, we conclude with a presentation of the same calculations shown word processed, but now using a spreadsheet. This is most likely the preferable option for engineers, as we can insert the appropriate formulae into the spreadsheet, and of course it will automatically evaluate the answers. Within this presentation, I'm simply showing the presentational format of the spreadsheet. And here are the approximate start times related to the various sections contained within the presentation, hopefully to aid your ease of access through the presentation, but please note all times stated are rounded to the nearest minute. So I'm just going to show you with this one calculation how I would structure this in terms of use of tables. You'll see in this presentation, to construct my solution, I will use the insert symbol menu. This will help me find Greek characters such as lowercase sigma. So clicking on insert and then clicking on symbol will bring up this box, and I can simply click on the required Greek character, lowercase sigma there, mathematical symbol, multiplication here, square root here, etc. and simply insert them into my text. So I'll make extensive use of this facility. Just a brief recap here from a previous presentation related to the precedence rules. Obviously, when we're typing our calculations, we have to ensure we always comply with the order of precedence, whether we're considering arithmetic or an algebraic, expressions, formulae, equations, and that's often expressed using the mnemonic BODMAS. This is an extract from our previous presentation here, so I'll let you review this at your own pace. Just a refresher hopefully here. Precedent rules continued. I do tendency to often think of the precedent rules in terms of a pyramid here. So when I'm considering my numerical calculations, I comply with the precedence rules by considering brackets as my first or top priority, operations, my indices, etc. as my second priority. But my third priority is division or multiplication because they have the same precedence. So in the pyramid, division and multiplication are in the same row. they have the same precedence. And the same with addition and subtraction. They're the lowest priority in my pyramid, but they both have the same priority. So I often do use the pyramid approach when I'm considering my precedence rules. But that's just for background reference. With the formatting I'm showing you in the tables, it's often more convenient to use one-line formatting for an equation, for an expression, than 2 lines. 2 lines can be formatted, but it's just more complicated in the tables. So again, some recap here. Being aware of our laws and our rules of indices can be very useful in helping us format formulae and equations into 1 line. Particularly useful can be the fractional index form, shown here, and the reciprocal index form, shown here. I'll try and highlight these as we require to use them. So I'm just going to show you with this illustration how I would construct and present my solution to other engineers using the word processor. If we just outline the question, we have a hollow cast iron tube that's used as a column member. The tube has an external diameter of 150 millimeters, a wall thickness of 15 millimeters, and we're asked to calculate the maximum load that the column can withstand if the compressive stress is not to exceed 80 meganewtons per meter squared. So that's the information given to us. Below is the solution that I've already outlined in the previous presentation, but now we're going to present this using a word processor. So here's my word processing screen. I've copied the question from our notes for reference. So to structure this, I would first of all insert a table with 2 columns. I would highlight the columns, I would move the borders from the columns, and I justify the left-hand column. The font I'm using here is Comic Sans MS. Just drag my column to the left here to merge the first row here. I like to number each of these steps in the process. I'm not going to bullet them now. So the first thing to do is to extract the information from the question. For reference, I will state my initial sign convention. So I merge this row here. So my sign convention, in this case, tensile forces and stresses are deemed positive. Just going to use shorthand notation here, so insert symbols, positive VE. Reading the question, the allowable compressive stress is not to exceed 80 meganewtons per meter squared. I use a Greek symbol here, so again insert symbol, find lowercase sigma here. I use suffix C to denote compressive stress, so 80 meganewtons per meter squared, so negative 80 multiplied by, and that's 10 to the power of 6. And from the insert symbol menu, here's the multiplication symbol, and that's newtons per meter squared. Again, I'm just going to use superscripts for the squared 6. We're also given in the question the external diameter of this tube, 150 millimeters, external diameter capital D, and that's equal to 0.15 meters. Because my stress is in meters squared, I'll ensure my dimensions are now in meters. And we're also given the wall thickness of the tube is 50 millimeters. I'm using lowercase t to denote the tube wall thickness, and again in meters that will be 0.015 meters. So that's all the information extracted from the question. What I always like to do, and I encourage students to do, is to now sketch the problem. So I have a sketch already produced, and I'm going to insert this into my table. I'm going to add some more rows to my table, so highlight my table, right mouse click, insert rows below. I'm going to split these rows here for the moment. So my layout option, split the cells, resize the right hand column here. I'm going to merge these rows and I'm going to paste in my image. So at the moment I'm going to leave that there. That's my little sketch of our hollow tube. The outside diameter shown in millimeters because that was given in the question, or thickness in millimeters. And we've got the compressive applied load Pmax. I'm now going to start to undertake the calculations. So I'm just going to highlight the rest of the rows shown here, drag them across to the left, give myself more room. So I'll merge this row. Let's consider step 2 of the solution. Here we're going to calculate the internal diameter, lowercase d. So initially state the formula. Internal diameter, lowercase d, is equal to the outside diameter, uppercase D, minus twice the wall thickness, 2t. Insert the numerical values. Outside diameter 0.15 meters, minus 2. Insert symbol times wall thickness 0.015 meters. Just label the solution by adding the next row. Don't really need that row, but shows my numerical working. So therefore the internal diameter is the shorthand notation for therefore is equal to 0.12 meters. When I undertake a calculation within the solution, I often highlight the answer using bold text here. This row here. Let's consider step 3 in the solution. We're going to calculate the cross-sectional area of the hollow column. Just need to resize my column slightly here. It's bigger. Resize my image slightly. Right, justify the image. So now I state the formula for the cross-sectional area of the hollow tube here, which is actually an annulus. So the area is equal to, insert the symbol for pi. Here's the pi symbol. Open bracket, the outside diameter squared minus the inside diameter squared. And that's all divided by 4. I'm writing the formula on one line here. Don't forget I need to use superscripts for my squared terms. And again on the next line I simply insert the values. So inserting a 0.15 for the outside diameter, 0.12 for the inside diameter. I can calculate the cross-sectional area, capital A. Just going to state the value this time. That's 6362 times 10 to the negative 6. Again, superscript for negative 6. And that's using 4 significant figures here. And of course that's now meters squared. And I'll bold that answer again. Going to need to insert some more rows here, so just going to highlight these rows, right mouse click, insert rows below. I'm going to merge a few more cells here. Highlight the cells, right mouse click, merge. I'm going to merge this row here. This will be step 4. In step 4 of the solution is to calculate the maximum applied load, labelled its Pmax here. To calculate Pmax, we're firstly going to state the formula for direct stress. I'm going to merge this row here. So from the direct stress formula, lowercase sigma, write it here, insert the symbol, lowercase sigma, is equal to the P divided by the A. Merge this row here. Rearranging for maximum load or force P max. Make that subscript. So on the next line, P max is simply the direct stress, or be a compressive stress in this case, multiplied by, insert symbol, the cross-sectional area. Again, I need some more rows here, so I'm just going to highlight these rows. Right mouse click, insert rows below. Now I'll calculate my maximum force or load, inserting the values. The stress we're given in the question, -80 times 10 to the 6 newtons per meter squared. Multiply that by the cross-section area, highlighted above here. So using my 4 significant figures for the cross-section area, that calculates to be -508,960 newtons. But for my practical purposes, that's approximately equal to -509 kilonewtons. And sometimes the final answer I not only bold, but I double underline. And I will state that's to 3 significant figures. Just drag my column here to the right. So for reference, that's how I would lay out my calculation on the word processor, essentially using the word processing table facility and using the insert symbol menu as required. There are obviously equation editors you can use to write the equation onto 2 lines, etc. And even in the table format you can actually write equation onto 2 lines. It's just a bit more complicated. But this is all I ever use when creating my notes or my presentations. So I'm not resorting to use of the inbuilt equation editors. Obviously the way I'm endeavouring to use the tables, the formatting of formulae or equations within one line is preferable. So I'm now going to show you some formulae where I have written the equations on one line, even if they are initially presented on 2 lines. I'll be drawing upon the knowledge of indices and fractions within this process. I'm also showing you the extracts from my word processor so you can see the way the tables have been formatted in the file here. So here's illustration 1. We're given this formula. U is equal to the square root of v squared minus 2as in the bracket shown here. So as an alternative, I could replace the square root with the fractional index of 1/2 here. Sometimes that can be written in this format here, which means the bracket again is raised to the power of 0.5 or 1/2, some square root in the bracket. So a slight variation there on the original formula given. Illustration 2, we're given that L is equal to GT squared divided by 4 pi squared. So formatted onto one line, the L is equal to the GT squared divided by the 4 pi squared in the bracket, notice. If I wanted to, I could replace the division sign, the slash sign here, with the -1 index. Because I'm actually dividing by 4, I can actually multiply by 0.25, multiplying GT squared by 0.25, and then dividing by the pi squared. Next, I've just used the -2 index. Instead of dividing by pi squared, I'm multiplying by pi to the -2. On the next line, if I wanted to, I can encase the t divided by pi in a bracket and square the bracket. And on the final line, I've simply raised the pi to the -1 index. So lots of variations there on how you can express the original 2-line equation formatted in this table here into 1 line. Illustration 3, this time we're given y is equal to 3 multiplied by in the bracket uppercase F minus lowercase f. That's all divided by L. So it's a two-line formatting in my table here. We could write that as y is equal to 3 multiplied by the bracket, and then divided by L, so that's one-line formatting. Or we could have the 3 multiplied by the bracket, multiplied by L to the negative 1. So again, given the initial two-line formatting, there's two different ways of expressing one-line formatting. And it makes it easier to construct the tables and present the calculation using the one-line formatting. But you do need to ensure always that your BODMAS is unchanged from the original given format. Illustration 4, we're given S is equal to v squared minus u squared divided by 2a. So from two-line formatting, you could write that as S is equal to v squared minus u squared. Notice that's in its own bracket, and now that's divided by 2a, and again I've shown that in its own bracket. Alternatively, we could raise the 2a bracket to the negative 1. So instead of dividing by 2a, we could multiply by 2a to the negative 1. Another option, because effectively we're dividing by 2, we could actually multiply by a half, and then just divide by the a. And the final line, we're still multiplying by the half, but we're now multiplying also by a to the negative 1. So 4 variations there on how you could express the original stated equation in terms of one-line formatting. Here's illustration 4 continued. Just be careful to ensure that the originally given two-line formatted formula, when rewritten using one-line formatting, we still comply with BODMAS. So again, considering S is equal to v squared minus u squared, or divided by 2a, our two-line formatting, we've already shown that this, with the v squared minus u squared in its own bracket, divided by 2a in its own bracket, is the correct formatting. Sometimes students will write the two-line formula in this single-line format without a bracket around the 2a, and they will undertake the calculation correctly. But you would need to be careful if you were typing this into a calculator. You would have to have v squared minus u squared in bracket, and you would have to divide by 2 and divide by a. So as I say, most students from my experience do evaluate this format of the equation for S correctly, but you do need to be careful, it's slightly ambiguous. However, this formatting for S is incorrect, as the precedent effectively resides with this part of the formula, so we'd evaluate the u squared divided by 2a, and then we would have to subtract that value from v squared, and of course that is incorrect. So I'm just highlighting here, we need to be careful when we convert a two-line formula into one-line formatting. We must ensure we comply with the precedent as stated in the original formula shown here. Illustration 5, again a two-line formula given for m. We can write it on one line by having our v1 minus u1 in terms of a bracket, so we're dividing by the bracket here. Or we could raise the bracket to negative 1 and multiply. Illustration 6, we're given time t is equal to 2 pi multiplied by the square root of L divided by G. I've actually used two-line formatting on the next line. I just removed the square root sign and raised the bracket to the power of a half. And if we consider one-line formatting, that'd be t is equal to the 2 pi multiplied by the square root of L divided by G in its own bracket. Next line, I've replaced the square root with the power of a half, or of course that could be replaced with 0.5 decimal. On the next line, I've raised G to the power of negative 1 inside the bracket, so instead of having L divided by G inside the bracket, I've now got L multiplied by G to negative 1. That's raised to the power of a half, or of course we could raise that to the power of 0.5. So again, slight variations in the way we could express the original two-line given formula in terms of a single line. Illustration 7, we're given that 1 upon f is equal to 1 upon u plus 1 upon v. That can quite easily be written on one line 1/f, 1 divided by f, is equal to 1/u plus 1/v. And I've also shown them in terms of the -1 index for reciprocal. So again, the given formula written on 2 lines is now shown written on 1 line in different forms. And illustration 8, I'll let you review this at your own pace, but again a 2-line formula for m. I've written in 2 different ways here. First 2 lines with the square root, and the second format here, just raise the bracket to the power of a half for square root. And here are my various single line formatting. Just note I have used slightly different styled brackets here. That's not essential, but that's just to help clarify the nested brackets used. So I hope these illustrations has enabled you to appreciate how we can rewrite 2-line formatting of a formula or an equation into 1-line formatting. And the use of word process tables, it does facilitate this method of presentation. And finally, just for your reference, we could of course use a spreadsheet to have presented a calculation. This is just an illustration to show what it would look like. Obviously the same question as before, but now I'm using the spreadsheet to present my calculation. And also, of course, the spreadsheet will undertake the calculation for me. So again, my step 1, extracting information from the question using Greek symbols as before. Step 2, I've calculated my internal diameter. Just notice I've written the formula I'm using here. Then the spreadsheet has actually evaluated the internal diameter d, given the information above. My step 3, calculated the cross-sectional area, and again I've stated the formula I'm using. Spreadsheet has calculated the area for me. And step 4, I'm calculating the maximum load. Again, showing the formula for Pmax, stress times the area. Again, the spreadsheet calculates the final load or force here. So that's an alternative way of presenting the calculation, and probably a more prominent method that might be used within industry due to the automation of the calculations. Anyway, I hope this presentation has been of interest to you in perhaps outlining an alternative way of coherently structuring your calculations using a word processor. Thank you for viewing.